Okay, in this particular problem, we're asked to find out some things about a battery. We're told the battery has a particular EMF and internal resistance. And then we're given some information about how much current flows when we connect various loads to the battery. The question is, what's the EMF and what's the internal resistance? So let's go ahead and take a look. We can draw what's going on. We got some sort of EMF that comes from the battery, and associated with the battery as well is some sort of internal resistance R. And I'll just draw a little box around. So this is actually the battery, so the unit. Think of it as this. Okay, this battery is hooked up to some sort of load resistance. There's a resistor here, and I'll call this load resistance R. And then the question is, given the currents for the various load resistances, what's the value of little r and the value of the EMF? Okay, in order to figure this out, we're going to have to relate the current that's flowing to the various quantities in the problem. So let's assume that there's some sort of current that's flowing around in the system, and it goes all the way around. And so what we're going to want to figure out here is, what's the relationship between the EMF, the current, and the various resistances? So I can start at this corner down here. I can go around the loop this way. And I can ask what happens to the voltage. So let's go ahead and do this, starting down at this little corner here. If I go up through the EMF, that acts as a boost to the potential. So I go up by value in voltage of the value of the EMF. I then go through a current, or a current goes through a resistor. That's going to result in a voltage change a la Ohm's law. And so voltage is actually going to drop by minus IR. As I continue around the current, I'm going to go through the big resistor R. I'm going to get another voltage drop, I times big R. And then I've come back to where I've started. And so I know that around any closed loop, the potential change has to be 0. So it implies that the EMF is equal to the current times R plus little r. Once we have this, it turns out we can actually solve the problem. Because I have a couple of different situations. One is I know that the EMF is equal to 0.4 amps. And I'll just go ahead and work in SI units here, and everything will be consistent. That's little r plus 25 ohms. Okay, so 0.4 amps when big R is 25 ohms. I also know that it's 7.78 amps when big R is 1 ohm. Okay, so I basically have two equations and two unknowns. In particular, just by examining the equations, I can see that it's pretty straightforward just to set them equal to each other. The right-hand side is equal to each other because they're both equal to the EMF. So I get the relationship that 0.4 times quantity R plus 25 is equal to 7.78 times R plus quantity 1.0. And I could solve this for R. I have to rearrange some terms and do a little tiny algebra. It turns out that this is 0.301 ohms. Okay, so there's a value of the internal resistance. Then once I've solved for one of the unknowns, I can solve for the other. In particular, I know that the EMF is equal to 0.4. Now this is amps, so this is amps times 25.301 ohms, which is volts per amp. And this is just little r plus 25. This implies that the EMF is actually 10.1 volts. And we solve for both quantities we want.